All right, so thanks for the invitation to give this talk. As the title says, I'm going to be talking about gradient descent with constraints. This is an example of what I think is a cute problem. I don't think I'm necessarily going to say a lot of new things, but I think it's cute. With that first, let me say what exactly gradient descent is, so that we're all on the same page. Suppose you have a function f, and it takes, let's say it maps to real numbers, so it takes a lot of variables and gives you a scalar function. And what you want to do is find the minimum of this function. And so maybe you just solve that ODE, right? So you follow the gradient, and this seems like a good idea to minimize a function. So suppose f is a positive function, then this would be a globally convergent algorithm. This is actually not what anyone uses because it's so slow. People tend to use Newton's method. But in terms of global convergence, this is the only algorithm that does that. From any starting location, it gives you convergence. Right? Newton's method doesn't do that. With constraints is to say that you actually want to solve this, but there's a constraint equation. So now it's not so straightforward. So you want to minimize f, but hold g constant. You can't just follow the gradient of f. You have to sort of project the gradient onto the space occupied where g is 0. So there's a whole literature associated with, how do you find a vector field on the surface that g is 0, so you can define a Riemannian metric on this and follow the flow. I don't understand a lot of those things, so I was like, well, there must be another way in which I can approach this problem and sort of understand it. So to do that, I'm going to take a massive detour and talk about a problem that's completely different. But I'll connect it at the end. Suppose you want to find the zeros of an analytic function. Okay, so f is a non-trivial complex analytic function. Non-trivial meaning it's not constant. If it's the constant function, there may not be a zero. Right, so you don't want to do that. So you want to find the roots. So you want to find ZR such that f of ZR is 0. There's a whole bunch of literature to review here. A lot of people just end up using Newton's method. You can use clever ideas, combining Rouché's theorem and the argument principle, and do like a divide and conquer algorithm where you take a domain and then you count the number of possible zeros there, and then you subdivide the domain till you find only one zero. Right? So Rouché's theorem and the argument principle let you count zeros of polynomials. My idea, because I like differential equations, was slightly different. I want to construct a differential equation for a point z in the complex plane, such that as time tends to infinity, the root is the attractor for this differential equation. Right, so that's what I want to do. Geometrically, the picture I have in mind is this. So f maps z to w. Let's say this is my starting point. So the point over here in the z-plane corresponds to the point over here. And I want to find the zero of f. Well, the zero of f is the origin in the w-plane. So that means why don't I just follow this path? Minimize v, hold u constant. Minimize u, hold v constant, right? That's the obvious path. So all you want to do is take the inverse map of this two straight line paths, and it might look like something like this, and there you go. That's the basic idea. So what I want is a differential equation that does this. I want a differential equation in the z-plane that follows these trajectories, right? So what are these trajectories? These trajectories are holding u constant or holding v constant. So let me just do the dumbest thing that I could think of, which was construct a Hamiltonian system where u is the Hamiltonian, So x and y are your two coordinates. So this is an even dimensional system, canonical Hamiltonian structure. Hold u constant, just follow that direction. Because it happens to be complex analytic, holding u constant is equivalent to going down following the gradient of v. Right, from Cauchy-Riemann equations, uy is negative vx and ux is vy. So basically, following the gradient of v is equivalent to holding u constant. So then I'll just play the game in the reverse order. Right, so I'll have two differential equations. One differential equation where I hold u constant, and another differential equation where I hold v constant. And I'll follow the path till I'm happy, which is to say, till I make v small enough here, and till I make u small enough there. Right, so turns out you can just use plain old Runge-Kutta 4 for this algorithm, and you get convergence. Right, so this is an example of a problem where you're doing gradient descent, but you have a constraint. You have to hold u constant. So there's a special structure to this problem that, because of the Cauchy-Riemann equations, we're allowed to basically solve problems like this. Follow a gradient, maintaining something constant, right? In the optimal control literature, this is called a bang-bang control because you basically change the differential equation at one given point. All of these differential equations roughly look like this. dz dt is some number times the complex conjugate of the gradient. Okay? This number can be plus or minus 1, plus or minus I, depending on whether you want to increase or decrease u, increase or decrease v. So you basically choose that. All it depends is which quadrant did you start off in. If you started off in the first quadrant, where u and v are both positive, then you want to decrease both u and v. Start off in some other quadrant, you may want to increase u or v. By the way, Newton's method has a continuous analog. You can actually rewrite Newton's method as dz dt is actually this thing. So Newton's method also has an ODE associated with it. You can see the primary difference between these two methods. Stationary points, when f prime is 0, are a big trouble for Newton's method. Right? They're poles. Stationary points are actually fixed points for me. I'll come back to why they're actually a good idea to have that structure. I just want to say a couple of things about the proof. I'm not going to go through the proof, but you can basically show global convergence, and you have to use the Little Picard theorem, which made me very happy because I've never actually used this theorem to prove something. So it's a really cute theorem that says, an entire function can omit at most one finite value. I have at least two possible canonical paths starting at any given location, which means I can always do this. There is always a path, there's always an inverse image for any path in the W plane I draw. I can find an appropriate path. And if the path exists, that means the solution to the differential equation exists, it will converge. The other thing, as I said, stationary points are where f prime is 0. Stationary points of my ODE, we know from complex analysis, they must actually be saddle points. If the order of the saddle point is n, then there are actually n plus 1 roots in the neighborhood of that point. This comes directly from complex analysis. So you sort of know something more when you actually hit a stationary point. So if you don't end up at the root, if you don't end up at the global attractor, you end up at the stationary point along the way, well, that's when you decide which directions to go and how many routes you want to spawn at that point, because you know there are n plus 1 sectors, n plus 1 directions that you could now go from that one stationary point to converge to others. Everything I said applies to a meromorphic function. Meromorphic functions may have singularities, may have poles, but the algorithm is designed to walk away from large values of f. So even if you start close to a pole, you will walk away from it. You'll never walk towards a pole. Right? So in that sense, it doesn't even matter that you can handle meromorphic functions. In fact, I did an example where you can actually make the algorithm go through the point at infinity if the point at infinity is analytic. You can actually go through the point at infinity and come back around to get to the 0. You have to be a little careful. Going through the point of infinity involves a coordinate transform. So after a certain radius, you have to say, well, I'm going to solve a differential equation, which is a coordinate transform, z to 1 over z, and then come back again. But that seems to work quite nicely. The big benefit of this is basins of convergence. Domains of convergence are smooth. This is not the case for Newton's method. Newton's method has very rough boundaries. They have fractal sets for boundaries of the domains of convergence. In my case, they're smooth because the domains of convergence are bounded by the level sets of harmonic functions. Level sets of harmonic functions must be smooth. So, which means I don't have to, I always know which zero I'm going to converge in. I can basically take the Riemann sphere and draw nice domains, and they just are a nice cover. No fractal sets, which means it's not pretty, but anyway. I just want to say for polynomials, life becomes much easier. You can actually come up with an algorithm, and you just play with the coefficients of polynomials, and you can get both the roots as well as the multiplicities. I don't think I have time to get into the details. The interesting thing to note with a polynomial, of course, is if you take enough derivatives of a polynomial, you have a linear function, and I know how to solve for the root of a linear function, and that's all I'm doing. I take a number of derivatives, I go to the linear function, that's this first step. Then I basically say, I'll use this as the starting point for my algorithm. Like I said, it's useful to have stationary points. In the neighborhood of the stationary point, there are for this guy, there are two directions in which I could go where I will converge to the zeros of the quadratic. And then from the zeros of the quadratic, I'll converge to the zeros of the cubic. And I'll keep going back up and up till I get all the roots that I want. Of course, this doesn't work for entire functions because I can never actually get. But if I had a single root of an entire function and I knew its multiplicity, then that's good enough, because now I can start playing the game. I'll look at the order of that root, and I'll know immediately how many roots there are in the neighborhood. I'll use that as a starting algorithm, and I can start going from one root to the other. And because I'm counting, by the way, if this is in exact arithmetic, in finite precision, you never really say you have multiplicity of roots. You just say there are so many roots in that neighborhood. They're close enough. You never really know that they're different. But you just say, well, there are 3 roots there close enough to the same point. But if you know the multiplicity, that it really helps. All right. So how does any of this actually generalize? This is great. This is cute. This is beautiful. But does it generalize? Right? That's the real question. What do I mean by generalize? This only works with a complex analytic structure, which means I can only be in 2 dimensions. What if I have a minimization problem which is not in 2 dimensions? How do I go further? And the key idea is actually to understand that there was a Hamiltonian structure here. It was a Hamiltonian structure, but just to point a certain fact out, u and v for the complex analytic function are not action angle coordinates. Even if you define the system such that u is the Hamiltonian for that system, if you look at v, v doesn't look like it's linear in t. So yeah, they are straight line paths in the uv plane, but they're not action angle coordinates. They are canonical coordinates, but they're not action angle coordinates. All right, so the idea is you want to generalize this trick with Hamiltonian systems. Of course, we know Hamiltonian systems, canonical Hamiltonian systems look like this, and they are always even dimensional. Well, that would apparently preclude me from ever doing gradient descent with odd dimensional problems. And that's a little unfair, because what if I have a function of 3 variables that I want to minimize? Why should I have to do this? Well, it turns out what you really want to do is look at a generalization of Hamiltonian systems. And there is a generalization called the Nambu, I think it's Nambu bracket. So Nambu introduced this generalization. So suppose you are in R3. So x is an element in R3, and you have two functions, h1 and h2, that give you scalars. If you take the gradient of h1 and the gradient of h2 and take the cross product, that defines a vector field, right? And it turns out that in this vector field, h1 and h2 are conserved quantities. So this is a generalization of a Hamiltonian system in an odd-dimensional space which has two conserved quantities, right? So if you're in three-dimensional space and you have two conserved quantities, that means you're basically a line, right? You're a curve. This system is integrable in a very trivial sense. You've got your two conserved quantities. You construct it that way. Turns out you can actually make a further generalization to an arbitrary dimension, n+1, right? Where you have the gradients of n Hamiltonians, and you use them with this some tensor S. So one example would be, the Levi-Civita connection, epsilon ijk. What does that mean? It means basically you're taking like a determinant with these columns, right? This is exactly the generalization of the cross product to higher dimensions. So it turns out if you consider this system has n conserved quantities, and it's in an n+1 dimensional space, has the same idea. You have a perfectly integrable structure. Yeah?
One problem. Basically, in direction, you learn that the Nambu-Poisson bracket boils down to Poisson.
Yeah, that's
the odd is fine.
For the odd, it's fine. That's right. So yeah, I'm only going to talk about ODEs in this case. And many integrable ODEs can actually be put into this Nambu form. You have to understand, of course, that if you are considering a Hamiltonian problem that you're going to put in this form, it may or may not be odd or even dimensional. You might introduce some Casimirs along the process. It depends on how you go about doing it. All right, so how can we use this generalization to solve our problem, which is follow a gradient. You want to minimize something and hold something constant. And the idea is we're going to use this structure to hold things constant, because immediately a dynamical system of this form has conserved quantities. So the constraints that I'm going to think of as conserved quantities of a dynamical system. That's what a constraint is, okay? So like I said, I want to minimize g of xy, and I want to keep f of xy constant. So allegedly, Nambu tells me I should look for something like this, right? It should be the cross product of the thing I want to keep constant, gradient of that, times something. And I don't know what that is. But I want S such that it should minimize g. So what I really want is, if I take the dot product of this entire differential equation with the gradient of g, I want this thing to be a negative definite quantity. It turns out this has a very obvious solution if you stare at it long enough, that S should actually be the cross product itself of the gradient of f and g. Okay? So it tells you the gradient Nambu system you want is the gradient of the thing you want to keep constant, cross product with this quantity, which would have been the vector field that kept f and g constant. Right? So what I'm doing is sort of this iterated bracket. So it's the tensor with this element that I want to keep constant, with the vector field that I would have got if I kept both f and g constant. So it gives this extra twist that keeps g, that minimizes g and keeps f constant.
Double bracket problem.
You basically get a double, that's right. You basically get a double bracket problem. That's right, that's right. So let's go back to the case of our complex analytic function where f is, let's say, u, g is v, and then grad f cross grad g is this particular combination. So it tells me my vector field, if you have followed through this calculation, it tells you that the vector field should look like this. right? You want to keep U constant, keep this quantity as such. You can actually use, if you use the fact that U and V satisfy Cauchy-Riemann equations, you precisely get the differential equation that I talked about earlier. Up to the factor of grad U squared, up to that factor. So if you actually wanted a pure Hamiltonian formulation, you just throw the scalar function that you're multiplying everything, the vector field by, just follow the direction. The vector field only needs to define a direction. You don't necessarily care about an overall magnitude of that vector field. Right? This is an optimization problem. We only want really directions. We're not so concerned about the magnitude of the vector. All right. Let's do this whole process again. Now let's consider, up to an overall constant of gradient of U squared. So I said it wasn't a canonical, it wasn't action angle coordinates, and there was that factor that you ended up with. That's the factor you end up with here. And then you can drop that factor because all you want is the direction. And it's just a scalar function that's multiplying a vector. It's a scalar function that, it's a field. It depends with, changes with x and y, but it gives you the exact direction you want. In fact, I should go back here, and when I said many integrable systems can be put into Nambu bracket form, one of the key things you need to know is what to divide the overall vector field by to get a particular Hamiltonian problem that you want. So that actually turns out to be a function of the various other action angle coordinates that you need. In fact, I think Rukmini's advisor was the one who showed one of those things. He actually wrote a very interesting paper where he puts a lot of different Hamiltonian problems into Nambu form, and you do need to find the overall constant to divide by to get the precise Hamiltonian that you recognize. Okay, so let's try this again in 3 dimensions, where now we will keep 2 functions constant and maintain and try to minimize a third function. And turns out you have to do basically the same idea, where you take the Nambu bracket of the things you want to keep constant, their gradients, and then twist it with what would have happened if you kept all 3 constant. And so this is the basic logic always, right? Higher dimensional generalizations are certainly possible. In fact, you might have a case where you're in such a large dimension that the number of constraints you have don't really fill the dimension. So you may be, let's say you were in 3 dimensions, but you only had 1 constraint, F1, and you wanted to minimize G. You actually have now a freedom to choose what to put in this column here. That's really useful because you could, at certain times, choose to put a vector that gives you an additional magnitude that makes you go faster or makes you go slower. Why would you ever want to go slower? Well, maybe you are at a region of phase space that's very stiff and that the vector field is turning very quickly. Well, maybe you want to take smaller and smaller steps naturally. So if you know that the vector field is about to make a very sharp turn in a direction, well, maybe you preclude that by taking gentle turns much ahead by choosing the appropriate constraint. You have now the freedom to do that. A classical problem in optimization is when you are in a sort of valley and you have like this long, narrow valley where in one direction there's very, very minimal change, but you can't really go in any other direction because you're stuck in a valley. And the gradient actually is very, very shallow in the direction of the minimization that you want to do. Well, you might want to actually accelerate through that point by choosing a different vector field that allows you to do that. So you can actually, having the extra freedom is really, really useful. All of this stuff that I said is actually a lot easier with tensor notation, and since I don't like tensor notation, I didn't introduce it. But I mean, it is the natural framework in which you want to do these things. By the way, a very cute thing to do is do the dual of this problem. Suppose you want to minimize F1 and F2 and keep G constant, right? Now what I do is I take a convex combination of the things I want to keep, things I want to minimize, and I'll keep G constant. I just reverse all our roles, and I naturally have this now additional freedom, because I want to minimize one function and keep another function constant. Right? So I could do the convex form. I could do different combinations. This particular formulation is really useful if you want to turn this problem into a numerical routine. If you want to do a numerical algorithm for this, you actually want to make sure that your numerical algorithm or your ODE solver maintains the constraints. Well, if you take a single time step, you may go off the constraint. So then you take a time step of this problem to go back onto the constraint equation. So what you do is you iterate back and forth between these two equations numerically. Numerically, a time step of this will minimize G, but may not keep F1 and F2 perfectly constant. So then you do a time step of this, where you choose T. It's like your trust region in optimization language, right? So you choose T such that you force the minimization of the errors now accumulated by going off the surface defined by F1 and F2, right? So you just iterate back and forth, and that seems to converge quite nicely. What's another application? Well, suppose you started off with a differential equation. How could you find its Nambu form? Right? And there's a very straightforward way to do that, where you look at the projection onto the orthogonal space of the vector defined by F. This matrix has n-1 independent columns. Just take, this is an n by n matrix. Just take any of the n-1 columns and stick them into this tensor notation. This is a Nambu form, but H1 and H2 are not necessarily gradients. They're not necessarily conserved quantities, but they are the directions you want to define. Maybe you take a linear combination of these guys and say, is there a conserved quantity? If there exists a conserved quantity, it must have this form, where this linear combination of the columns of this matrix must be in the form of a gradient of something. Which means now you have Liouville type or Frobenius type integrability theory to rely on. When will the coefficients, when can I choose the coefficients such that this combination is integrable, right? So a lot of classical theory immediately comes into play, and then you can say, given a vector field, how do I find the associated conserved quantities? Life is a lot easier if this is a polynomial vector field, in which case you can choose alpha j's to be polynomials, and then you just start matching coefficients, right? This gradient condition, you can use the Frobenius integrability conditions, and then that's just a system of equations on the alpha j's, or the coefficients of the polynomials of alpha j's, and it all works out really well. Here's a quick example. So suppose you had a Hamiltonian system, and I played the same game. The orthogonal projection to the vector with minus HQ minus HP, if I follow this principle, it gives me basically the orthogonal vector should look like this, HP squared HP HQ. And that's proportional to HP HQ, which is the gradient. So it recovers exactly what you want. In higher dimensions, the algebra is a little more complicated, but for all the systems that I discussed, you can actually go back and start off with the Nambu form and say, what are the associated conserved quantities? They're exactly what you would get. And in the last minute, I'll just briefly mention what I'm nowadays looking at, which is how do you write differential algebraic equations in this form? So a differential algebraic equation is one where you have a differential equation and some additional constraints. Now the differential equation has a parameter z, and x and z are related by these constraints, right? So ideally, I would just like to have a single vector field that naturally has those constraints. So I want to embed these constraints into a new vector field for x and z, where I will now put these as constraints, and I need to find out what S1 and S2 and all the way, these additional columns, such that this whole vector field looks like or is proportional to F. that's where I'll end it. Yes, this can be done. I should just say that the reason I haven't mentioned any results is I've basically recovered what people already do. So it's not particularly interesting, but at least I'm on the right track. And I think I'll stop there. All right, thank you.
Thank you very much. Question? Okay, just go 2 steps behind. I've asked something. Back. Yeah, just 1 second.
Oh, the question wasn't for me. Oh, that's fine. I see.
Equation? No. But Harvey Brown? Harvey Brown? It's a gradient type of structure. This is the structure.
You had a question?
Yeah, why not call it
Because you have some algebraic constraints, right? So it's a differential equation with an algebraic constraint. Doesn't have to be, I mean, it doesn't have to actually be an algebraic function. It can be some transcendental function. Most often what I've seen is usually it's an algebraic thing. Really, I think that's right. Yeah. The most natural explanation is suppose you have, a pendulum that's oscillating. There's a natural constraint that the length of the pendulum must be maintained. So that's what this guy would be. If you go to the right coordinates, of course, we know that the pendulum is a Hamiltonian in a different coordinates. But if you just stuck to xy coordinates in the Cartesian plane, then you have to actually maintain the constraint equation that x squared plus y squared is a constant. So if you wrote down the equation for x and y, then x squared plus y squared must be a constant. That's where these sort of systems naturally occur. In a sense, if you do a discretization of Navier-Stokes, this is the incompressibility equation, right? This is a divergence free. It is a constraint that must be satisfied for a flow. And this constraint is somehow telling you about the other variables which are not getting time-stepped. So pressure in incompressible Navier-Stokes doesn't get time-stepped. It satisfies a a Poisson equation. And so you can think of the divergence-free condition as telling you how to advance the pressure, Z, in my case, to the next time step. And that's really what I want to do here. So I'm really looking at, ideally, a discretization. So if you take finite element approach to Navier-Stokes, can you embed the constraints that you have as a vector field, rather than actually enforcing the solution of this system for Z at every time step? Yeah. Mm-hmm. Yeah. I think so, yeah. 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 Yeah.
What you were asking, there was a nice thesis by this thing. Here are these things. I'll talk to you. It's a very beautiful paper. But I have a serious question.
That was also a serious question.
Also look and look at all of them are see, if I change RA
Yes.
to group manifold, what will happen? Are
I,
you able to do that?
I don't know the answer to that question.
If I change to RA to a group manifold,
I don't know the answer to that question. If I can define the gradients, yeah, sure. I mean, that's.
here guessing.
That's.
So is that my hunch is basically go to the adjoint action.
Yes.
What is the for you this one general case go to the trilinear algebra.
Mm-hmm.
Trilinear algebra of this. It's a better number of the people use for the actual action might not just become like that. Okay, that's very good. Excellent.
Thank you.